And hello, today AP students. Now we get to the fun part. How in the heck did I get those x, v, and a equations for simple harmonic motion? How did I come up with this? That's also really important. All of your simple harmonic motion equations will come down to this. They should look like this in the end. There's another format I'm going to show you in a second that they should look like. But really, all simple harmonic motion will come back to your period. Okay, how long it takes is generally what we care about. It'll always have 2 pi because it always has to do with that angular frequency. So here's your amplitude, here's your time, right? It'll always have to do with basically how long does it take to go from point A to point B. Same point on the curve, right? Same point on the wave. So 2 pi will get you there. That's your 2 pi. All right, to there. And for a spring, we're going to talk about springs first because that's actually easier. And I want to step you through this to show you kind of clearly how I come up with this first before you dive into pendulums, which is a pain. You got to use forces of tension. And as you remember on that one, you got to find your x and your y as you go through. So you got to find both of them. And then you got to sub the y in for the x. It's a long process. But we'll get to that next. So joy, 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 okay? But here we go. So for springs, we need to get to this. And we know for every spring that we have, its periodicity has to have something to do with maybe how far you stretch it. But really, it has to do with how fast it's going, right? It has to do with the stretchiness of the spring, right? It has to do with the mass, you kind of a mass that you might hang off of that spring, like so. That was totally worked. If I put this in here, that would change the periodicity of the spring. So all these things have to figure it into it. In the end, what really matters, the only thing that matters is the mass on the end of the spring, dangling from the spring, right, or attached to the spring, and the spring constant. So why does the amplitude not matter? The starting position not matter, right? Why do those things not matter? Why does the velocity of the thing not matter? Isn't that kind of weird? So let's figure that out. Okay, so here we are. So first things first, okay? If I have a spring, like I do, and I hang a mass from it, well, I want you to think about in terms of forces what's happening here. What's pulling the mass down? It's gravity, isn't it? Okay, so acting downwards from this mass, I'm going to give it a little more room here. So from this spring here, there's a mass on the end of it, and acting downwards, we have the force of gravity. What keeps it from falling? Well, that has to be the force of the spring itself, holding it back up. So we have the force of the spring holding it back up, and those two things are in equilibrium. So what does that mean? It means that they just kind of hang there. They cancel out. So it means those two forces have to be equal. Those are the only two things we have to consider right now, okay? So this is why it's easier for a spring. So let's figure this out. We know the force of the spring has to be equal to the force of gravity. Okay, so that's not too bad. So force of the spring, if you remember Hooke's law, that is negative kx, right? Distance you stretch the spring by is your x, okay? K is the stretchiness of the spring, constant of the spring, okay? And it has to do with gravity, okay? So on here we've got gravity. Let me make sure I'm not already screwing something up, checking my notes. Yep, all right, so mg, right? Now here's the thing. We know that any force is equal to a mass times acceleration, right? So really, what we have for this spring, okay, in any circumstance, even if you're not on Earth, okay, so let's go ahead and change this. Let's just call it a force. What if we're taking and stretching the thing in a different way? If that's the case, if it is gravity you're working against. If it's not, though, they can still use springs in space to measure weights of things, which is kind of cool. Masses of things. And the way they do that is you can attach a spring to an unmoving point, right? Stretch the spring out. If that's the length that it wants to sit at, when you stretch it past that length, right, with a mass on the end of it, it will still oscillate back and forth. If you're on a frictionless surface, it'll do that for a while too, just like it does here with gravity, okay? So it will still want to oscillate this way. Now, the force bringing it back this way is the force of the spring. It's always a restorative force. It wants to kind of pull it back to where it was, right? And this force here would have to be the force that you exerted. So again, it's not force of gravity here. Now this would just be a force, okay? So I'm going to make it more generalized. Force of the spring okay, force of the spring is equal to the force, whatever it is that stretches the spring, okay? So if you stretch it out, the spring is now counteracting the force that I'm giving it, okay? So these two have to be equal, so negative kx, stretchiness of the spring constant, distance you stretch it by, has to be equal to whatever any force is equal to, which is always ma, right? But let's put them on the same side and make it look a little more interesting, okay? So if I put this over here, I will get 0 is equal to mass times acceleration, or force, plus kx. Okay. Why did I just do that? That's interesting, but, what does I get? Well, we're going to find something out here, okay? And if you remember, a is actually the second derivative of x, right? A is the second derivative of x, okay? So it's actually, if I write that correctly, it's actually x double prime, okay? So acceleration is the second derivative of x, okay? So let's go ahead and take a look at that. So this becomes a lot more interesting suddenly. And that is what we're going to have to use in a second right up here, okay? So as I march through here, what I want to do is, let me check my notes again so I stay on track here. I don't waste a bunch of our time. What I want to do is think about those equations of position, right? Let's think about our equations of position. The position that this spring is in here, right? If I pull it down a little bit, it can't go any farther down than that. It can't go any really higher up than that. So the amplitude, the distance I stretch this thing, has to, its x position over time has something to do with that amplitude I give it, okay? So x, as a function of time, has to have something to do with the amplitude, how much I stretch it out, basically, okay? And it always comes in, it's a cycle, okay? It's a cycle. It will go up and down. So for amplitude and our time here, if we plot those, right, it goes up and down, up and down, up and down, up and down, right? So it'll always do something like this, okay? Its position will always change as a function of time, okay? And it will never stretch beyond the original amplitude you give it. So it has something to do with a sine curve or a cosine curve. Let's go ahead and start with cosine, just see where that gets us, okay? And it has something to do with other things that are going on here too. So it has angular frequency. How long does it take basically to go through that? What's its speed essentially, right? Its speed to go through one full cycle. So it has something to do with its speed to go through a full cycle. It certainly has to do with time. Speed and time will tell us exactly where we are no matter what, right? Okay, and it also has to do with where we start our like stop motion camera here, right? If we start our camera here, well, we can still measure our angular frequency and figure out our position. It doesn't really matter. If you walk in the room after I started this experiment, you can still do the experiment without knowing my initial point, which is kind of cool, right? So all your phi right here, that weird looking symbol, that Greek symbol phi gets you, is basically where in this curve am I starting? Am I starting here? Am I starting there? What's my starting point, right? So this is your offset or your phase shift, okay? It's how much do you shift that wave around to make that your starting point instead of this, okay? That's all that phi gets you. Okay, so there is our x equation to find our position. So that's how I worked it out. Working it out just from kind of general principles of what should matter in this thing, okay? So we want to go and figure out our acceleration, which is our x, double dot or x double prime, however your notation works, right? So our second derivative, we want the second derivative of that thing. But do we get to the second derivative by doing the first derivative, right? So let me move this up on the board, copy it down so it's first off actually straight on the board. Okay, so a cosine of omega times t plus phi. Make that look a little bit better, maybe. There we go. All right, so now we got to do our first derivative, and our first derivative of position is velocity. Yay! All right, so if I take the derivative of this, first off, let me do this. Derivative of cosine is sine, but it turns negative, okay? So I get negative, keep my a in there, it's not going anywhere, right? And it turns into sine, okay, of something that's in here. But before I actually do that, I screwed up, didn't I? Okay, so we're going to do that next. All right, so before I do that, we got to keep a in here, because a is just coming along for the ride. We're doing this derivative with respect to time, right? Function of time. So with respect to time, I have to deal with this first. Constant, nothing, goes to 0, right? Now that has a derivative because it is stuck with time, okay? Because it's a function inside of here, this time is only going to shift our cosine to sine, and this is just going to pop out our omega. So we will get a minus, you'll see why the minus in a second. Our omega pops out, and our cosine goes to a negative sine, okay? And then everything else remains the same inside of here. Nothing else in there changes, okay, for this derivative. Okay, and there you go. So now we got our velocity. Big whoop, right? We didn't actually care about that too much. It's interesting, and actually it is very useful to figure out how fast this is going at any point in time, right? But what we really don't want to find out is we wanted to get to our acceleration. So now we got to take the derivative of that guy. Second derivative of this one, first derivative of that one, okay? So we had A keeps coming along for the ride here. We had a negative, okay? So now again, same deal. We have to take the derivative of there, and guess what? Same thing happens again. Still a constant, still respect to time, it does something with respect to time. So we still pop out an omega. So now we get an omega squared, right? We had an omega. I added another omega to it. We get omega squared. Okay, and then we go from sine to cosine. And when you do a derivative of sine, you do not flip signs. So we don't make it another negative, okay? It still just says sine, derivative of sine is cosine. Derivative of cosine is negative sine, okay? So that's why we got the negative here, but we're not switching our sign now, okay? And everything else that's in the middle of this still remains the same. So there is our acceleration function, and that's really where we wanted to get to. And now here's the cool thing. Check this out. We have A, we have cosine, we have omega t plus phi on the inside. Look at x, A cosine omega t plus phi. That is very similar to that, isn't it? So we can summarize this acceleration. Acceleration, if we're going to take and substitute this into it, look what we get. We get negative, because this was positive before, we have to keep track of our negative, okay? We get negative, omega squared wasn't in it before, but everything else was. So omega squared times x is our acceleration. Kind of cool, right? Oh, okay, big deep breath. Now we're going to use that, and we're going to come back into here, okay? So remember, A is x double prime, and that's what we got to sub in. We got to sub something in here, okay? So now, that's what we do next. Okay, so let's come back to here. 0 is equal to, instead of ma, I'm going to plug this in place of a. So it is m times omega squared x, okay, plus kx. Well, now let's take and move this to the other side, shall we? Okay, so let's move this over, and we will get, voila, like that, okay? So x is on both sides. It now goes away, all right? So let's say I wanted to figure out what my omega was, okay? If I wanted to find omega, now I have to take and divide over my m, okay? And I want to find omega, not omega squared, so I have to take the square that was on my omega and square root that side. So it turns out my angular frequency, I can find that for any spring, simple harmonic oscillator that is a spring in this case, right? My omega, my angular frequency, is my spring constant divided by my m. Okay, so that's interesting. I'm going to erase this side now, so you might want to pause and write all that stuff down, okay? But I'm not going to. I'm going to run through. All right, so, okay, so here's another thing. We wanted to get to period. Remember, that's where we started out. So we have to use another equation here. Period is equal to 2 pi over our angular frequency, okay? So for one full cycle, what is our angular frequency? That will give us our time for one full cycle. Up and down, pendulum, back and forth. But again, this is a spring, so it's up and down or back and forth for stretching a spring out, okay? So now let me take and plug in for omega here. Okay, fun. Well, I'm going to simplify this down. I'm going to make it t is equal to 2 pi times 1 over omega, okay? for 1 over omega, I get the inverse of that. I flip everything upside down, right? So really I'll get 1 over omega. So omega was square root of k over square root of m. And since it's 1 over, I just have to switch everything around. Okay, so I'll get square root of m over square root of my spring constant, or simplify it because they're both square root of m over k. Just that flipped upside down. Right? So now look at how I got to my period for a spring. Kind of cool, right? Sadly for you, that was the easy one to do. The ones we're going to get to next. But make sure you got this, okay? Period of a spring has everything to do with the mass and the spring constant of the spring. Cool, because you can use this in space, right? It has nothing to do with gravity, okay? This is actually how they weigh things in space. They can actually figure out the periodicity, how long it takes for a spring to go back and forth, right? If they know the k value of that spring, they can find the mass. So that's how they weigh things on the space station.